Okay, you can start. Thank you.
Okay, so let me start over. Thank you very much for being here and good morning, everybody. It is a pleasure for me to introduce Niccolo Bucciantini. Niccolo is a senior scientist at INAF Arcetri, working in Florence. And we have been working together since almost 2 decades now, quite some time. And we have been in contact for different projects and different research ongoing. He's an expert on Pulsar Wind Nebulae, on pulsars and related stuff, both from the observational and the theoretical point of view. And historically, he has seen significant contributions in HT and MHT simulations, the first, or one of the first, very detailed simulations of the cracked Pulsar Wind Nebula, with all the torus, the jets were done by Niccolo and his team. Niccolo got a PhD from Florence and then went to several different positions. He spent several years as a postdoc working with Jonathan Arons, which is another expert on pulsars, now retired, was working in Berkeley. And then he went to Sweden with a fellowship in the group of Axel Branderkuk, that is a person working on several different fields, including the sun, our sun, related to magnetism, HT, MHT simulation. And lately, in the last few years, he was very much involved with IXPE. IXPE is a satellite that measures detailed maps of polarizations of different systems. So I thought it was a good idea to bring Niccolo here. Thank you very much for coming to tell us about the most important results of this study.
Okay, thank you, Diego, for inviting me here and all of you. So the idea is to give you a brief review of the status of the art of a Pulsar Wind Nebulae in the light of IXPE. I assume you hear lots of talk where people explain to you how things now works fine. I will try to tell a story of how things now don't work so fine. So a brief introduction for those of you who are not familiar with the field. So stars more massive than about 8 solar masses ends their life in supernova explosion. And if the mass is below a threshold set at around 25-30 solar mass, these explosions leaves behind a compact stellar remnant in the form of a neutron star. These objects are typically very rapidly rotating. The crab rotates 33 times per second. Other systems can rotate up to the millisecond period. And they are endowed with a very strong magnetic field, typically 10 to the 12 Gauss, 10 to the 11, in the case of magnetar, 10 to the 14, 15. Now, the result of rotation and strong magnetic field is to produce a very strong electric field at the surface that can pull out of the surface of neutron star charged particles. Even ions, but mostly electrons. These electrons are accelerated in the pulsar magnetosphere. They undergo a pair cascade process. And the result is that out of this pulsar, you generate a wind, an outflow, mostly made of pairs, electron and positron in a magnetic field that can reach relativistic speed. Now, when this outflow interacts with the environments, it creates the Pulsar Wind Nebulae. The Pulsar Wind Nebulae is nothing else than a wind bubble inflated by this relativistic pair outflow from the pulsar. Why do we care about these systems? Because these are beautiful laboratory in the galaxy to study high-energy astrophysics. There are many other high-energy astrophysics environments, if you think about it. There are gamma ray bursts, there are accretion disk around black hole, but they have a great disadvantages. They are far away, and it's very, very hard to resolve these systems, spatially resolve these systems. So to understand what is happening where. In gamma ray bursts, we don't even know where particles are accelerated, at what distance exactly, how these things is happening. These are galactic systems. They are close by. They are very easy to observe, let's say, and they are very well constrained. In the case of the Crab Nebula, we know almost everything, probably not all the things we would like to know, but lots of things. We even know exactly the date it was born. It was, I think, the 4th of July of 1054. These systems have been observed virtually with every single telescope that was ever built. The Crab Nebula is probably one of the most observed objects in the sky. If you do an ADS search, probably it's the most cited object after the sun. So in reality, we have a very beautiful place and a very good way of studying these things. These are important for understanding various theoretical aspects of high-energy astrophysics. non-thermal radiation process, and particle acceleration are the most important. The fact that we don't understand particle acceleration in systems that are well constrained tells you a lot about how we don't understand particle acceleration in general. If we were able to have a good model for particle acceleration in this object, we would be just a step forward in understanding how to apply these to other environments, like, for example, GRB shock. These are also relativistic systems in a certain sense. So let's go and look at what we know of this object, and I will discuss what is known as the canonical model of Pulsar Wind Nebulae. This is a model that has emerged in the last 26 years since the launch of the Chandra satellite. It's a combination of good observation and state-of-the-art numerical model for these systems. So one thing to look at is this is the spectrum of the Crab Nebula. This is just a synchrotron component, the low energy. The first things that one notice is that this is the most complete non-thermal spectrum in the galaxy. There isn't a single Maxwellian to find anywhere in these systems. This is a spectrum that extends from the ionospheric cutoff. Essentially, it's not possible to look at lower energy just because the atmosphere is opaque, all the way, in this case, to the maximum synchrotron energy at 150 MeV. Synchrotron particle cannot radiate above that point. There is an extra component that is not shown here, that is inverse Compton, that goes all the way to PeV energy, or something above PeV energy. And again, you cannot go beyond that simply because the universe is opaque for higher energy photons. They don't reach there. So it essentially covers everything that we can supposed to be observed. And the spectrum can easily be described as a set of broken power law with various breaks, explains in various ways. But the point is that it is fully non-thermal, and essentially almost the entire energy injected by the pulsar in this system that is radiated in non-thermal energy. Because it's the most efficient accelerator ever. Now, why is it important to study these systems at different wavelengths? This is an image of the crab at 3 different wavelengths: radio, optical, and X. And you will notice immediately the vast difference in morphology. If you look at radio, you are looking at low energy emitting particles. Typically, these have a very long lifetime for synchrotron emission. They fill the entire nebula. So what you're looking here is the morphological volumetric structure of the system. Very amorphous, some filaments, very extended. When you go in optical, you see also line emissions. These traces essentially the material in the inner layer of the star that is now photoionized by the synchrotron component of the PWN. So out of the thermal emission from these lines, you can learn, for example, that the progenitor star of the crab was most likely a low-mass star up to about 13 solar masses, because the ratio of carbon over oxygen is not very. And the other is X-ray. X-ray is fully non-thermal, and you immediately see the difference between the fully non-thermal wave. This is because X-ray particles are particles that have a very short synchrotron lifetime. Essentially, you are seeing particles that were injected at most 20 years ago. They trace the injection condition now. So they are a probe of what the wind and the pulsar are doing now in the nebula. And this funny morphology, which is known as jet core structure, this main torus plus a jet, is essentially a probe on the properties of the wind itself. Now, we understand this morphology as a tracing the condition of the pulsar wind. So we can use the depth to constrain the wind and ultimately constrain magnetosphere and the working of the pulsar. We know this also from the fact that when you look at the crab at different energy, you see that as you move to higher energy, the system shrinks inside. Low energy particles are very extended because they essentially, we are looking at particles that have been there since this system was born. High energy particles have a short lifetime. They are only found close to where they are accelerated. And indeed, this is telling you that particles are accelerated close to the pulsar. So acceleration happens in the central region. It also tells you a very important lesson, that if you just study radio emission in these systems, you learn nothing of what's happening to X-ray particles. It's very, very hard from these to get something like a look like this, or to even guess there is something like this. So radio is not very informative if you want to study acceleration as it happens now. It might be very informative if you want to study the global evolution, the history of the system, but not acceleration properties. If you want to do acceleration properties, you have to move to very high energy. Oops, sorry, this one. Now, this is not, this funny structure is not just typical of the crab. It is virtually seen in every systems where we have deep enough Chandra images to study them. So it's a very common feature. It's not common in the sense that it looks always the same, right? There are systems that are jet dominated. There are systems that have strong ring, a couple of rings, single ring. the idea is that somehow the difference in morphologies might raise a minor difference in the pulsar property. Maybe they have different inclination angle, maybe they have different magnetization. But overall, the fact that we do see this jet and torus structure in all systems is telling us that there is a common basis on which we have to model all of this. And this common basis ultimately is set by the dynamics of the pulsar wind. Now, exactly in the same times where we were developing model for the nebula, people working on pulsar magnetosphere were developing model for pulsar magnetosphere. These are old models, a force-free model, the first one that were developed. Today, we have even better models that include percreation, that include charge-started magnetospheres, that are able to compute also emission and light curves on top of it, you can name it. But the point is this: you have a very fast rotator at the very center that produces a wind. So what you expect a relativistic version of what is commonly known in space plasma physics as the Parker spiral, the structure of the solar wind pushed to relativistic. Far away from the light cylinder, which is the region that characterizes the closed magnetosphere of the pulsar, or rotating region, the wind would like this spiral structure that propagates out. Now, if you have a fast rotator, you'll imagine the magnetic field is all wounded up, it will expand, it will fly, and will pile up inside the nebula. So what you imagine is that the structure of magnetic field in the nebula should reflect the fact that you are injecting from a compact rotator. And indeed, this is what is seen in some systems. Now, the pulsar is here. The white line traces the magnetic field. It looks like nice loops that pile up into the nebula. So, okay, everything fits. The beer is there. You find an object that matches your theoretical expectation, and you might be happy. But I will show you later that you should be careful of extending too much what you see. So, in the meantime that we had this X-ray observation, we developed numerical model to try to rebuild or simulate what we were observing. So the first numerical models, essentially what you do, you put your pulsar at the center, you decide where your injection, you blow a wind, and you see what happens. You will create a cavity, you will shape the dynamics of the cavity. So in this case, we have a pulsar at the very center. We have a wind that, according to people working on pulsar magnetosphere, should be stronger on the equator and weaker at the pole. This goes through a shock. It's a relativistic wind, but ultimately it will have to expand at the expansion speed of the PWNe, which is a few thousand kilometers per second. This shock is not spherical, it's oblate because of the energy distribution. At the end of the deal, out of all of these, you will create a complex structure of velocity flow inside the net. So if you use a model, very complex model, you get something like this. You have your central wind in red, and here as velocity flow channel. Some of this matter will manage to flow on the equator. These will give you the torus. Some of the matter will, because of magnetic effect, be recollimated toward the axis and give you a jet. Problem is, this is a velocity map. We don't observe velocity. I would like to observe velocity. We observe synchrotron emission. So you have to take this and turn into a synchrotron map to be sure that what you're actually seeing makes sense. To do this, you need to attribute to each point of your simulation a synchrotron emissivity, and then integrate. How you do this? Well, you take a recipe for how particles are accelerated along the shock. You evolve this distribution along your streamline, and in each point of your box, you can compute a local emissivity. Then you take a relativistic equation, you boost it, you put your observer in some direction, and you figure out what comes out. And if you play a bit with the parameter of the simulation, with the inclination, with the recipe for the emission, you can get something like this. This is the result of an emission map from simulation. This is the central region seen in optical by HST. Every single feature that you have here is qualitatively mapped to a feature that you see up here. So you have the torus that's here, it's in this region. You have this wisp region here that looks like this. Notice that there is a wisp here with a negative wrong curvature. They look like this. You have a bright spot, it's not seen here, which is the knot of the pulsar very close to the pulsar, which was not clear how you would get something very close to the pulsar. You get a bright spot here. This is the region here, is the anvil. You have this counter wisp that sits here. Essentially, qualitatively, you match. Maybe not in terms of quantitative brightness, but in quality. The good point of having a simulation is that you can play with it. what I can do, I can switch on and off or turn on and off a piece of my simulation and see which features disappear and which doesn't. So I can identify in my simulation what is producing what. For example, I know that this knot, which sits very close to the pulsar, is not actually sitting close to the pulsar, it's just a projection effect. It comes from a region, a very high latitude region of the pulsar wind termination shock. The wisp instead comes from a low latitude region. Now, if I can identify where along the shock this various feature comes from, now I can correlate their property with the property at the shock. And so if I have different spectral properties, I can imagine this different spectral property to be due to different acceleration properties along the shock itself. The knot is very highly polarized, which tells me that there is lots of ordered magnetic field here. The wisps are far less polarized, still high polarized, but far less, which means that here probably you have more turbulence at the very beginning. You can even look at what kind of slope the spectral shape and check if, for example, acceleration of particles in this region proceed with different mechanisms in this out. So in principle, you can do tomography of your shock with this. So everything works. If you can work tough and hard, you can manage to do things. But there is a devil in the details, and the devil is that you have to assume an injection. You have to assume a recipe for accelerating particle at the shock, and this is where the problems sit. There are essentially two recipes in the literature for accelerating particle at relativistic shock. One is standard DSA, diffusive Fermi acceleration. What you do, you have particles that bounce across the shock, and crossing the shock, they gain energy, standard picture. Except that in relativistic shock, this doesn't really work. The reason why it doesn't really work is that pulsar wind are supposed to be strongly magnetized or decently magnetized to produce the structure that you see. So particles are attached to magnetic field line, and if you work out the math, the pulsar wind are in what is known as a superluminal condition. Particle cannot manage to jump back across the shock. Particle can cross the shock a couple of times through a drift process, but then are advected in the downstream. If you do that, you get the zero acceleration. So the result of these simulations, that peak simulation, is that you can get a direct shock acceleration in paired plasma system like a PWN, only if they are weakly magnetized. So weakly magnetized that if you want to have your spectrum, you get nothing else. You don't get a jet, you don't get a torus, you get that the overall spectral injection breaks. So maybe this works, but it cannot be the main acceleration process in the nebula. It works locally in some patches, but definitely not everything. Now, given that this doesn't work, people have tried to come up with a different recipe, and the different recipe is reconnection. So the idea of reconnection is quite interesting. Now, you have an oblique rotator. Your pulsar is not aligned, it's hardly aligned, otherwise it won't be a pulsar to begin with. So the point is that in the equatorial region, you will have that your wind has this alternating polarity because the pulsar flips. So you have this striped wind. You have wind of alternating polarity. When it reaches the shock, all these stripes are compressed. This is a relativistic shock. So compression factor scale as the Lorentz factor. And if you compress magnetic field of different polarity, you can imagine what happens. You will get force reconnection. You will drive tearing mode instability. And you will create lots of turbulence in the downstream. This turbulence is very good at accelerating particle. Now, how it accelerates is still a bit of an issue. It might accelerate because it creates electric field. There are on-screen electric field in the current sheet that might potentially accelerate particle very efficiently. There is nothing more efficient than an electric field to accelerate particle. But it can also create bigger merging island, and particle can be accelerated because these islands tend to converge to each other. So particle will start to mirror along the island and get accelerated through that. This is a different process than DSA, it's more a kind of Fermi one. What is the good of this? The good of this is it's very efficient. A large fraction of the energy can convert into accelerated particle, on top of which it can give you very hard spectra. DSA typically comes out with a universal spectrum. It's typically -2 in non-relativistic shock. In relativistic shock is -2.2, 2.3, something like that. But radio particles have a much harder spectrum. Reconnections and tearing modes in driven accelerations can give you much harder spectrum. What is the problem with the reconnection? The problem is that if you want to have the spectrum that we see in PWN, with acceleration efficiency that we see in the PWN, we need to impose conditions in the pulsar wind that are completely at odds with the pulsar magnetospheric model. There is one parameter in the pulsar wind which is known as the multiplicity. It tells you how many pairs you create for each electron that you extracted from the pulsar. You have a pair cascade. Now, all magnetospheric models that exist in the literature give a number of order 10 to the 5. For each electron you pull out of the surface, you create 10 to the 5 pairs. If you want these mechanisms to work, you need a 10 to the 8. You are a factor of 1,000 wrong. It's not just a problem that it doesn't work with our pulsar magnetospheric model. If you put too many particles in the wind at the base where you launch it, the result is that the stripe disappears before they reach the termination shock. So for the stripe wind reconnection to work, you need to put so many particles that you don't have a stripe wind to begin. That's the entire problem. So it's a promising, but from a theoretical point of view, is setting very, very tight constraints. So the hope was, okay, we have an MHD model. We know how to locate pace on the shock. Now, if you're smart enough, I can do tomography of the acceleration along the shock potentially. And by looking at a single feature, I will tell, okay, look, this looks exactly like DSA, and this looks exactly like acceleration, and this probably looks something we haven't thought before. But it didn't really work that well as we hoped. So what is the good of this? Well, the good is that our model, with some recipe, acceptable recipe, can reproduce very well what we observe. This is an image of the crab in X-ray. This is the best I have been able to do in the past 20 years. Essentially, it matches. Qualitatively, you get an exact match. More or less, features sit where they should. Now, this is the good. The bad. The bad is that, unfortunately, you match in a qualitative way, but not in a quantitative way. The first problem is you immediately see the difference between these two if you have a keen eye, is that simulations are very bright on the axis of the net. The torus is very bright in the front part and very faint on the side. This is not the case in simulation. You have a much more shallower luminosity profile. It's not a kind of, okay, that's a minor issue. It's not a minor issue. If I want to get to these kinds here, I don't get to this feature to begin. So it's not something that you can easily accommodate in simulation, the intensity value. The other issue comes from variability. We know these systems are variable. This is the movie based on a simulation. You will see lots of variability going on. The problem is that it's too much variable. We know that this system changes, but changes in the luminosity amount to few percent. The changes in the luminosity there amount to 100%. So the time scale of variability is correct. A few years, the amount of variability is completely screwed up. This is telling you that our simulations somehow have more order than what we would expect in reality. They tend to be more variable, if you want, and they have this more enhanced luminosity structure that doesn't correspond to reality. Of course, many of these simulations are 2D, so you know the answer, right? Okay, it's 2D, the world is not 2D. You go to 3D and everything will be solved for you. Going to 3D is very, very difficult. It is very, very demanding, and it's not guaranteed that it will work for you. Moreover, the problem with 2D simulation is that given that these are magnetic field is fully ordered, you get incredibly high fraction of polarization. In the X-ray, we know in crab is 20%, and there is no way of going below this. Magnetic field is stuck there. So you don't reproduce these things. So you go to 3D and you hope that 3D will solve all your problems. It solves some of the problem, but not the one you care about. So the problem is this. This is a 3D simulation. This is the structure of the magnetic field. What you can immediately see is that overall you have lots of mixing in your system. That's fine. Magnetic field is unstable. It drives mixing. There are various kinds. But if you look at the central region where X-ray comes from, it doesn't look very different from 2D. The central region in 3D is telling you that 2D is not a bad approximation of the central region. Not terrible. So if it's not a bad approximation, all the problems will not be solved in 3D. And indeed, if you look at 3D, what you have is that all the problems related to variability remains. 3D variability is very strong. It's even worse than 2D variability because now you have patches on the sides that flashes up and down, which you see nothing of this in the card. And in some sense, it's even going to overshoot what you expect. Now, even if you don't see much of 3D effect here, if you measure the integrated polarization in 3D, you get values that are always below 15%, which is not what we see. We see values of about 20. And I can assure you that when I say below 15%, it means that it's below 15%. It's not that, so, okay, sometimes you have 20, sometimes you have 25, sometimes 15. No, it's sometimes you have 10, sometimes you have 7. If you are lucky, you get 15. So the large-scale 3D dynamics is not the solution of the problem of acceleration. So that will not make your simplifying canonical model match the result of observation. There must be something in our model that we are missing. And the idea for a long time is that we are missing unresolved turbulence. 3D simulation have finite resolutions. They are already demanding. So that's something you cannot get all the scale that you need, but you know the plasma will develop a long turbulent cascade. So there must be some unresolved turbulence. What are the evidence of small scale turbulence? Well, from numerical simulation, we see plenty of vorticity in our life, plenty of eddies that form and develop. From an observational point of view, I think the best evidence for the presence of small scale turbulence is the gamma ray flaring observed in the crab. So these are events where the gamma ray 150 MeV luminosity of the crab went up 25 times over quiescent emission over a time scale of a few days. Now, to get that, to produce something that looks like this, you need to accelerate particle to very high energy over a very short time scale. So you need very strong current sheet over regions of a few daylights. The only way to get something like this is through a process known as turbulent intermittency. Turbulence produces a cascade. Intermittency tells you that there is a finite possibility, a much higher possibility than what you would expect from Gaussian statistics, that locally you will have a high deviation from the expected mean. And so you can have locally very strong current shift. And these, if they reconnect, will give you your flares. So this is one evidence. A very old evidence of the presence of turbulence in the system was the ratio of the size of X-ray and radio. I told you that X-ray is smaller than radio because X-ray particle lives very little, radio particle fills everything. If you take a laminar model, standard Kennedy-Coroniti laminar model of the PWN, you can advect particle, you can compute their cooling times, and you can check what would be the size of the X-ray with respect to the radio, and it doesn't work out. The X-ray are much more compact than the radio in the laminar mode. So if you want to match the X-ray, which are very far extended, almost close to the very edge of the radius, with the radius, you need to add extra diffusion for high energy particles. Extra diffusion means a few times bomb in the X-ray to match the relative size. How you get a few times bomb, and you need to put turbulence of some sort inside your systems on the scale that are relevant for X-ray particles. These are not the large scale of the nebula. X-ray particle sample scale of order of 10 to the 16, 10 to the 15 centimeters. So you need to have turbulence on that scale. So how do we include turbulence? Well, thank God there are simple recipes to plug the effect of unresolved turbulence into synchrotron. So what I can do, I can take my simulations done without turbulence and add the turbulence in post-processing and see how my map will come out if I forgot turbulence inside. If I do this, this is something that I get, for example, for the Crab nebula. This is the Crab nebula. This is a simple torus in synchrotron emission. If I add turbulence, given that synchrotron cares about the total energy, not the geometry of the magnetic field, I can make my systems look more like the Crab, less concentrated on axis, more extended, more loaded. I can lower the average PD. So I have been toying in the past a lot with this simple prescription to see how I need to add turbulence, resolve turbulence to make my simulations fit my observation. And typically, you get values of delta V over V of order 1 in order to get this. So you have some of a claim of the level of turbulent energy that you have inside. It's true that this is speeding, but at least things work out. The problem is that this is just a toy. Okay, you can do little with that. To show you why, the problem stems from the fact that synchrotron emissivity is very, very blind to the magnetic field. This is a PWN, is MSH 1552. This is a jet-dominated system. Now, I can make toy model of this very easily. These are 3 toy models that have been built with 3 very different recipes for the structure of the magnetic field in the jet. One of these has a purely radial magnetic field in the jet, fully ordered. Another one has a purely toroidal magnetic field in the jet, just small loops. And the third one is fully chaotic. Now, if you have a very, very keen eye, you will see there is some difference in the luminosity profile of the jet. But now imagine putting these into a real object, where you have a background that's not uniform, the system is not straight, it's not exactly axisymmetric. Which one will you pick? Moreover, which one would you guess is what? Okay? It's very hard to tell, right? So this is the answer. So the point is that toying with the luminosity can help you a little bit, but ultimately there is too much degenerate. You can't really work out this. So we need to be able to actually measure the geometry of the magnetic field. And to do that, you need to do polarization. Synchrotron is the only possible way. Problem is that we have plenty of polarization measured in radio. Radio gives you polarization almost for free if you measure it the right way. And as I say, there are systems where the structure of the magnetic field you get from polarization fits the bill. This is the beautiful case, fully toroidal, high polarization. This is ideal. You get this, you present at your talks, you say, I have this model, this is the data, everything works, my model is successful. Except that, unfortunately, radio polarization is all over the place. This is a purely toroidal magnetic field. Change object, you get purely radial. This is G21.5, and the magnetic field doesn't loop the loop at all. But don't worry, theorists have an answer for these too. And the answer is, we are looking at particle at the edge of the nebula. The edge of the nebula is unstable. There is so-called related instability. Matter penetrates, magnetic field gets stretched. We are looking at radial magnetic field because there are fingers of matter that protrude inside and stretch a magnetic field. Fine, beautiful. So let's look at two systems where we do see these fingers that penetrate inside. The Crab Nebula and 3C58 is a beautiful finger. You actually see them. So they should have a beautiful radial structure, right? That's what theorists tell you. You do the Crab and it's fully amorphous. The polarization in the Crab correlates with nothing. It doesn't correlate with the radio emission. It doesn't correlate with the X-ray emission. It doesn't correlate with the position of the pulsar or with the symmetry axis of the system. It's the way it is. And the same for 3C58, where polarization follows some loopy structure throughout the nebula. There is no evidence of toroidal structure, at least from radio. There is no evidence of any radial structure. If you look in optical, at the very center, you will see that the structure will look more like toroidal, which already pointing you that the radio doesn't tell you much. But the worst thing is that not only doesn't tell you much, you have no idea what it's telling you. Is it telling you it's very stable or it's very unstable? Why do you get amorphous? Why do you get radial? It's not so obvious. So the radio polarization is not informative at all, not even on the global structure of the systems, unless we don't understand how it originates. So we have to look at X-ray. And the problem with X-ray is that X-ray polarization has been measured for the first time in the Crab in the 70s to the OSO satellite. It's an integrated measure that for some reason nobody did anything. So the first measure of polarization in these systems came back, space resolved, thanks to IXPE. IXPE is an X-ray satellite. It's a 3-mirror module. It was specifically designed to do space-resolved X-ray polarimetric measure. Now, this is a list of the properties of IXPE. I will focus on 3 of them, which are interesting for this business. One is the polarization sensitivity, measured to the minimum detectable polarization. It tells you how long you have to integrate or observe in order to get at least something. Polarization in X-ray is a photon-starved technique. You need to accumulate lots and lots of photons to see a beautiful modulated signal. And the point is that these objects are not very bright, apart from the Crab, which is really shining, but all the other PWNe are marginally bright. So unless you have an object that can provide you some good numbers in a reasonable time, then you do nothing. Just to give you an idea, typically a PWN will require a megasecond of observation to get the signal. And I'm talking about the brightest in the clip. The other important thing is angular resolution. Of course, we don't have Chandra angular resolution, but that's out of the business. So, but we need at least some resolution to resolve the inner structure. We don't want just to have an integrated measure, because integrated measure in a systems where you have toroidal structure or amorphous structure will be very small and you will learn nothing. The third point is the energy band. Now, IXPE worked exactly in the same energy band as Chandra. And this is a plus for our source, because then you can use Chandra as a fiducial high-resolution map or structure of what you are observing. I can take a Chandra map, associate a polarization structure, send it through the image response function of IXPE, and get what IXPE should see. But I can also do backward folding. I can take what IXPE sees, use a Chandra map as input, and figure out how polarization should be distributed in order to get back. So I can put polarization to single structure in the Chandra map in this way. Not with a high accuracy, because PSF is PSF, but the point is that I can at least attribute it to the torus, to the jet, and other things. Okay, so I will discuss a couple of objects which I think are very important to tell you how this result has somehow changes the picture that we have of the system. One is the crab. Now, the crab was the principal object observed. It was the first PWN. And what you see here on the left is an image, the intensity of the crab. Overlaid is the structure of the magnetic field that we get from polarization. So in X-ray, you do see a magnetic field that exactly matches this toroidal pattern that we were expecting from theoretical models, despite the fact that the radio is totally amorphous. So it's a very ordered geometry. It matches very well the symmetry axis of the nebula. So the structure of the magnetic field follows quite well the symmetry of the entire system. There is evidence for polarization in the jet. And more recent measures have shown that indeed the jet seems to have a toroidal magnetic field, and instability in the jet might be more likely associated to kink instability than others. But things change a lot if you look at the polarized fraction, which is, if you want, a direct measure of the level of turbulence that you have in your system. First is that the structure of the polarized fractions doesn't match at all the symmetry of the nebula. You have a very highly polarized patch in the north and the south, actually not even at the torus, at the outskirts of the torus in the north and the south. You have a very low level of polarization in the center, where you're injecting things and where you would expecting a higher values of polarization based on optical data. But more important, you get lots of variability even across. Interestingly, despite the fact that there is a very high level of polarization on the north and almost no polarization on the east, in terms of emissivity, there is not much different from the north side of the torus and the east side of the torus. So for some reason, I don't know, turbulence managed to distribute itself such that the synchrotron overall emissivity doesn't care much. But this is telling you that if there is turbulence in the system, this is far more patchy. You can't just take a recipe and say, I have a uniform emissivity like the one I did, and work with that. You have not a uniform turbulence, and so you have to cross-correlate the various things. It's not so. In the case of crab, we have also good measure of polarization on the pulsar. And what we found is that the pulsar have a very low level of polarization, and ultimately only the main peak is polarized with a polarization of order 15%. Now, this is a very interesting result because there have been various models of pulsar emission presented in the literature. These are a very old set of models. This is inner gap, outer gap, slot gap, and strike. But there is a common properties of all models that invoke pulsar emission, this is X-ray emission, coming from the inner magnetosphere. They all make prediction of a very large polarized fraction, between 80 and 60%. This is what they predict. In the inner magnetosphere, you have little turbulence, magnetic field is very ordered, produce emission, this will have a high level of polarization. We see nothing of this. The best we see is in the center of the peak, in the interpulse region here, where most of these systems predict a very high polarization. The polarization is less than 20%. So basically, just this measure allow you to say that models that invoke a pulsar emission coming from the inner magnetosphere can be ruled out. What you are left is with models that attribute emission coming either from the light cylinder, the very outer magnetosphere, or the wind itself, which is not something that people typically think. People typically think that emission will come from the poles and not from the wind that sits somewhere else, but it's possible to do pulse emission in the wind. So these are the only one that survives, but they barely survive. So to show you why they barely survive, it's very easy to make a wind semi-analytical model of the pulsar wind. This is the so-called stripe. Okay, this is the so-called stripe wind model of the wind. There's a beautiful analytical solution that describes the structure of the current sheet. This is a simulation. This is the analytical solution. It fits quite well. So you can take that solution and compute on top of that solution the light curves that you would expect. It's complicated. You have to take into account retardation times, the fact that things rotate, whatever. But this is just the business of your codes, handling things, and you're writing the equation properly. And this is what you get in terms of light curves. The dots are the X-ray data, and the blue and yellow lines are two models of emissions that have been able to work out using this very simple semi-analytical model of the wind. Now, if you present something like this, you will say that you have almost a perfect match. Typically, matching light curve of pulsar is not so good. You can manage to reproduce the intensity difference between the main peak and the interpulse. You manage to reproduce some of the emission. It's true, it doesn't fit very well, but who cares? You will think that this is a very successful model, right? We reproduce the light curves. Good. So let's look what happened when you compute polarization on top of this. And this is what happened. The blue line is what you predict, and the points are what you observe. The orange in optical, the green in yellow, and wow, it doesn't. There are 2 points. First, this is not even the original prediction. In order to put this line within this range, -20 + 20 of the Stokes parameter, you need to depolarize the signal by about 75%. So you need to add the unresolved turbulence in your analytical model of the current layer of the wind. But even if you do that and you manage to reduce the level of polarization in the range you measure, you don't really fit the data. Maybe you can somewhat perhaps fit the main clouds, but I would say no. So polarization is a very constraining probe of the pulsar magnetosphere, far more constraining than light curve. Ultimately, the reason is quite simple. In a light curve, let me go back, the separation of the peak is just a matter of inclination geometry. No matter what your model, you fix the inclination, you get the separation. The width of the peak is just a matter of regulating the size of your emitting region. What is really difficult to simulate is the relative intensity of the peak and the relative intensity with respect to the bridge. And these are typically things that don't work out. Model of pulsar typically have 2 peaks which have the same strength, which is not observed. Polarization is far more constraining because it makes a lot of difference if your magnetic field is this way or this way. It makes no difference in terms of radiation, but it changes everything in terms of polarization. So it really is a probe of the structure of the magnetic field where you are in. The other object I want to discuss is Vela. Vela is a system that when you look at it, it looks exactly like cloud, more or less. And if you apply the toy model with unresolved turbulence, you get exactly the same number. You get a large level of turbulence in order to reproduce the feature. Then you look with IXPE, and the result is that you get polarization in certain spots that are almost up to the theoretical maximum foreseen. This object has no turbulence whatsoever to be found. Except that when you look at it, it behaves exactly like the crab. It accelerates a spectrum that's no different than the crab. It produces the same ring as the crab, but it has no turbulence at all. Worst of all, these objects show in X-ray exactly the same magnetic field structure that is shown in radio. The white lines are radio magnetic field. The dark line are X-ray magnetic field. They map on top of each other, and not just for the central region, also all the way down in this extended halo. Vela is an old system, is interacting with the supernova remnant. The supernova remnant is pushing part of the PWN away. And all out of this old mess, you have no turbulence, and all the radio particles look at the magnetic field that you infer from radio look exactly like the magnetic field you infer from X, which is not what you get in crab, which is completely different. This is a funny point because I recall you that this is how the systems look in radio. Forget about this. It's very bright here and very bright here. There is absolutely nothing to be observed in the central region. This is how it looks like in X-ray. There is something here, there is nothing there. So despite X-ray particle and radio particle living in different places and tracing different portions of the nebula, somehow the magnetic field that they come out is exactly the same. And there is no evidence of turbulence or change between these two. So this tells you a lot because you have two systems that look very similar, but in terms of polarization are complex. The last things I want to discuss are Bow-Shock Pulsar Wind Nebula. These are Pulsar Wind Nebula that form when the pulsar managed to escape the supernova remnant and penetrate the ISM. And what we know is that in a few systems, we have plenty of these cases. In a few systems, we observe these strange structures, these jets, float particles that are where they should be not. pulsar is moving in this direction. You would expect particle like a comet to be in this, and instead they shoot 90 degrees away. Same for the lighthouse. There are other systems. This is the G327. Pulsar is moving in this direction. You will assume everything drifts from the back. You have a particle shooting in front. And you have other systems where you see halo instead of seeing jet. But there is evidence of particles escaping out of the systems and escaping in direction where they should be. The problem with this feature here is that if they escape in the ISM magnetic field, they just fly away. Fly away tens of parsecs, hundreds of parsecs away. They don't stay there. So in some way, you need to confine the particle there and enhance the local magnetic field. Now, we have been able to measure polarization in a few of these systems. The first one was at the center of the galaxy. You have all these filaments in the galactic center. And the idea is that this filament could be something like we saw before due to pulsar that moves in the magnetic field and leave particles. There is one in particular, G0.13, where we have a spot here and the X-ray feature here, and there are several radio filaments there. The idea is that you might have a pulsar here that's moving in this direction, is producing these jets. These jets create an X-ray particle, and as they cool, they might give rise to these fainter radio halos on the back. So we managed to measure the polarization of the diffuse emission of this system, and the answer was that this is a very highly polarized, 50-something%, and the magnetic field is aligned with the feature. So this is a clear evidence that X-ray is a synchrotron emission, and it fits the bill of associated, but there's a very high polarized function. Recent measure on the lighthouse have confirmed this picture. This is Chandra, this is IXPE. Of course, quality is different. We have a measure of the magnetic field and the polarization in the feature. The magnetic field is aligned, the polarization is about 50-something%. So very, very high. We even have polarization in the body. And again, the polarization is aligned with the tail. Polarized fraction is small, about 30%, and is exactly orthogonal to what you see in radio. In radio, you have magnetic field that goes this way. In X-ray, you have magnetic field. Which again tells you that even in these systems, you can't trust the radio to provide you an idea of what is the global structure. The problem with the feature is that the very high level of polarization that you have is totally incompatible with theoretical model of socket. These are particles that escape. If you want to confine them, you need to have a high level of turbulence. The only way to make a high level of turbulence, much higher than the local ISM, is to drive turbulence through streaming instability that will help particles to self-confine. This is the standard model. You need a very high magnetic field, you need lots of turbulence to produce particles. These particles stream, excite waves, they resonate with the waves, they amplify their own turbulence and get stuck there. Fine, in order for this to work, you need delta B over B of order 10. If you want to get this polarization, you need delta B over B less than 0.3. So, if you want your theoretical model to work, you can't reproduce the polarization. If you want if you translate this polarization into a level of turbulence, you're not able to confine particle there. Somehow, nature managed to do both. So, this is the point. Okay, I'm concluding. So, just to make a point, we do have a good model of PWNe. We have a canonical model we trust. We think we understand how it's working. It provides us a good overall picture of what's happening, but polarization came out not to match exactly our expectation. It fits some of the bill, but it creates problems. It adds an extra level of information, extra observable that's hard to match with our general understanding. It's not even clear what is the relation between turbulence and acceleration, because as I show you, there are systems that looks in terms of accelerating particles the same, Bill and Crab, and in terms of polarization properties are very different. So whatever is accelerating in the two systems must somehow either be uncorrelated with the level of turbulence or work no matter what the turbulence is, or perhaps we haven't been able to look well enough. We are still working with satellite that has a 30 arc-second PSA. Okay? Polarization is highly constraining. I would claim that for the way we are now, we can't claim a good match in the case of Pulsar, but even of Pulsar Wind Nebulae between theory and data unless we also match polarization. I mean, it's not something that we can keep on the border just because we don't know how to manage it. and then keep pushing light curves over light curves. This is something that sits there. If you have a code that produces light curves and has a magnetic structure, it can produce polarization. You better see what comes out. The other point is that there is a large diversity in the field. IXPE has opened a new window. Unfortunately, it was designed to be a discovery mission. So the idea was just get the first measure of this system. We have been able to observe 5, 6 objects overall. The brightest, I think that IXPE has ended essentially its lifetime in terms of the PWN. All the other systems that are available are much fainter, and already the one that I've shown you have all 1 megasecond observation. I cannot go there and ask them 5 megasecond observation of an object, because that will be equivalent to ask them to give me IXPE for half of the year just to me, and it's never going to happen. So the point is that if we want to move forward, we will have either to increase sensitivity, but I think it's very, very important also to improve on resolution. Not much. I don't claim that we need to go to Chandra because that would be funny, but at least push it down to, let's say, 10 arcsecond resolution will be more than enough to clarify some of these systems. Increasing the effective area or increasing the sensitivity by a factor of 4, there are mission proposals for that, would be enough to set some of these issues because there is still a lot of uncertainties. For example, in the lighthouse that I showed you before, measuring 50% plus or minus 20%. Okay, you know what it means. It could well be 0 at the end of it. Okay, so these are basically my correlation, and we need further modeling for the Pulsar and PWN in order to be able to understand what we are observing, especially the fact that radio and X-ray gives very different. And that's it. Thanks.
Thank you very much. Very nice talk. If there are comments, questions? Yeah.
Thank you very much for the next talk. I have two questions. Like for the carbon nebula, I don't know about this. Is there something different in the environment? And you also show like the gamma ray emission, like with, for instance, with COSI, we will be able to constrain it more to the gamma ray polarization.
Okay, so for the environment interaction, Vela and Crab are thought to be different. Crab is a very young system, 1,000 years old, and it sits at the very center of what we think is its supernova remnant. We don't see the supernova remnant in Crab. We see nothing of what surrounds the Crab, so it's a bit strange. And so basically, we don't expect the interaction with the environment to shape it dramatically. We do see lots of instability arising because it's definitely close, it's well resolved. Vela is an advanced evolutionary stage. It's about 11 kilo years old. Is interacting with the supernova remnant. If you look at the supernova remnant in Vela, Vela sits at the very edge. And perhaps I have even a slide. I'm not sure. Let's see. Okay, this is it. No, I have to unskip. Okay, this is the complex of the Vela. Here you have the X-ray PWN, which is interacting with the environment. And we think we know it's interacting with the environment because this is the gamma ray PWN. So these gamma ray are inverse quantum. They are produced by low energy electrons that upscatter the CMB and the galactic background. So if you think about it, you have the pulsar that's moving in this direction. Here you have a freshly injected particle, and there is a leftover PWN on one side. The idea is that, in a certain sense, something is pushing everything down. So you see only energy particle here, where you have PWN, and low energy particle down, where you actually have been pushed the low energy particle. So this is an interacting phase. And this interacting phase, you would expect this interaction to actually trigger lots of turbulence and of mixing. You are having your pulsar smashing against the supernova remnant. In reality, you have a much cleaner environment. It seems that most of the turbulence, if there was any, was being pushed away, and the system has retained a lot of its clean environment, which is not what we expect. I mean, if I do simulation of bow shock, I don't see clean environment. You see plenty of turbulence developing, even more, because now you have a wind that pushes against something, hits it, magnetic field is forced to be compressed even more, and it tends to reconnect. For the COSY argument, yes, because unfortunately we have a big hole in the MEV region in the study of PWN. I think the older results are Egret and Comptel, which are sparse point, and I don't know even how much I should trust the normalization, the flux calibration of those instruments. COSY, I think, is a bit low energy because it's around 1 MeV and a bit below. Probably for CRAB, it would be better to move to 10 MeV region. This is a very interesting region because you are looking at the cutoff in the high energy particle injected is also the region of the flare. And being able to characterize PWN in that region will enable to understand A, what is the maximum energy the particle can achieve at the shock, B, if you have flaring in other systems. Now, it's very hard to see with COSY flaring in other systems because I think the effective area is not really enough. But at least the object like astrogam, which didn't fly through, but the class of astrogam object, it's what you would need in order to be able to sample that region. We have a hole there, so our model just arrives at new star data, and then there's a hole, and then you start with Fermi on the other. For the CRAB, it's still fine. CRAB get to 150 MeV. Fermi can manage that region too. But for other systems, for the cutoff with lower energy, 10 MeV, 1 MeV, you need objects that work in the MeV energy.
Other question, Han?
Yeah, thanks a lot. Fantastic overview. So I have very simple questions. You mentioned what was very high difference between the polarization of that, very interesting. So, and you mentioned it's, I understand correctly, that there's a fractalization with the typical Pulsar models that very well ordered building layer experiment. Now, my question is, what if indeed, in practice, of the age of the system, the formation takes for several reasons? Actually, the magnetic field in the electromagnetic field is not what it is. Okay.
Yeah, it's
that's all.
Okay. I don't know. The answer is I don't know. The point is that probably if we had some magnetospheric model, because the point is that all these light curves that I will show you are built on standard back on the envelope Dodge solution, force-free solution, simple magnetic field structure. There isn't much of a machinery in investigating what happens if you have a multipolar structure at the surface, if you have twisted magnetic field, for example, things like that. It's not really being investigated a lot. Mostly because I think the interest has gone in recent years to gamma rays. And most of the work in simulating light curves focus on those pulsar, both from the numerical point of view, because you have good light curves, and because there you think you understand the physics a bit better. For example, I will tell you that I'm not even sure if you are looking at synchrotron or inverse Compton in optical and X-ray. This is the entire point. You could get light curves that look exactly like the CRAB I show you, assuming that the emission is synchrotron, assuming it's inverse Compton on a local background. Get excited. So you can think what is the uncertainties. My point is that I would like to take some of these simulations and see what comes out in terms of a polarization. The winds is very favorable. I mean, now it goes as the most favored magnetospheric model emission, but for the CRAB, I have a polarization of other system like MSH 1552, for example. We have some hint of polarization in Cas75. These are weaker. They tend to fit the rotating vector model, which is what you typically use. So even in pulsar, it's not obvious that all pulsar produce radiation in the wind. The wind works very well for CRAB, but for other systems where you have maybe a single pulse broad, rotating vector model seems to fit the bill to a certain extent, which means, and these are not older or younger. For example, Cas75 is not older than CRAB. It's a magnetarish-like system. The pulsar in MSH 1555 is a high B pulsar. It's not magnetar-like, but it's high B. So I don't know if this is telling us something peculiar, or at the end of the day, it's really every pulsar goes its own way, and some of them manage to have high multiplicity and radiating the wind, the other maybe have a different structure and radiating the inner magnetosphere.
Any other comment? To me, it is very striking that at the level of flux of emissivity, you get essentially the same flux is completely uncorrelated with polarization.
Yes. There is some minor, very minor correlation. I'll try to see if I can show. Okay, this patch is slightly brighter than this. It's about 50% brighter, except that this is 45% polarized, this is 0 polarized. There is also a difference in spectral index. Here is a bit harder, here is a bit soft. Now, if you imagine that soft and hard goes with having more magnetic field that dissipates, less magnetic field that dissipates, something like that, you might claim that turbulence correlates with spectral index. Now, I'm not showing it here, but there is an object. Let me see if I can pick this up. And I haven't, no, I haven't, no, I don't have it. So in MSH 1552, for example, there is we have a measure of polarization in the jet. So MSH 1552, let me go back, is this object here. Is jet dominated. And there is a very funny thing if you look at the spectral index in the jet. Spectral index is very, very hard at the base of the jet. It's even harder at the base of the jet, or almost similar to what you have in the torus. In our model, magnetic MHD model, the jet typically comes from matter that flows to the nebula and recollimates. So typically we get a very soft spectrum because this is matter that has moved a lot in the nebula. And by the time it reaches the base of the jet, it's already old. So it's already lost. It's very, very hard to get the very high spectral index that we get here. So 1.6, this is very, very high. Now, the particle index. What we see in polarization is that this is the base of the jet is strongly depolarized. Then you see polarization that increase along the jet. And the key idea is you have lots of magnetic turbulence at the base of the jet. This magnetic turbulence is what is causing the depolarization on one hand, but what is causing on the other reacceleration of a particle. And so it's keeping your spectrum hard. As you move along the jet, polarization dissipates. So the turbulence dissipates. So polarization increases because you are left with the residual magnetic field, and you get the softening of the jet spectrum. But this is just words, right? We don't have models that plug in and get numbers. This is just an heuristic of what we observe. So we're trying to make sense of what we observe in this. So there might be some correlation between the hardness of the spectrum that you observe and the level of turbulence, but
how much, is there another question? Just final short question. How much of the large scale polarization that you see in X-rays would you say it can be ascribed to injection process? Or
all of it.
All of it is
all of it. All of it. So the point is that with IXPE, I mean, I would claim that apart from the crab, where you have enough counts that you can do localized stuff, in all other systems, for the way IXPE works, because it has a finite resolution and the sensitivity not that much, what we are actually measuring is really the central region. So in systems, for example, like 3C58, we have integrated measure of polarization, because that's the only things we can get. But that if I use the Chandra map, and I plug a polarization recipe in a Chandra map of 3C58. Let me see if I can get the just. Yes. So basically, this is 3C58 in radio. I don't have the X-ray, but the point is that the X-ray is a very bright jet torus structure at the very center, very confined. So if I fix the polarization in the jet torus structure, no matter what I do in the surrounding of the nebula, polarized, unpolarized, take the radio, make it constant, I always get the same number once I fold into the IXPE. So essentially, I am measuring, even if I get integrated, I'm actually measuring only what's happening in the center. To get the edge, I need an instrument that is at least an effective area which is at least 5 times or 4 times above X. Otherwise, I mean, in this object, I have probably some 10,000 counts, of which 1,000 comes from the central region and the remaining 1,000 from the boundary, and they are nothing to the overall result.
Thank you very much again. Any other final comment or question? Yes?
I have questions. I'm not entirely sure it makes sense. Anyway, so throughout first of all, thanks for the talk. Throughout the talk, you mentioned turbulence as maybe a key aspect in explaining what these things, in some system works, in other it doesn't. Now, my question is the following. In MHD turbulence, I believe we don't know much, but we don't really expect MHD turbulence to be universal. And so, for example, I think you mentioned that in some system, the relative magnitude of the magnetic fluctuations over the background is 1, or in some other system is 10. I wonder, because the relative intensity of the end tells you about how anisotropic MHD turbulence is, and I wonder whether this may
Okay.
part of the puzzle. So
that might be part of the puzzle. So when I'm talking about a recipe for including magnetization, I always try isotropic turbulence. So the recipe assumes isotropic turbulence. We know that turbulence could be anisotropic. The problem is that how much anisotropy you want to put in. I mean, in principle, toying with anisotropy, you can do lots of things. You can even have a fully turbulent system that look highly polarized just because your turbulence is all in one direction and nothing in the other, right? So you can play these games. The problem is that we don't know exactly how this happens. Typical simulations seems to lead to some different in scale, but not that big, unless you have a very small level of turbulence. So if you have a delta B over B is 1, then it's almost isotropic. If delta B over B is smaller than 1, it's almost anisotropic, but at that point, if delta B over B is much smaller than 1, you are polarized. So you don't care about the isotropy much more. It's not very relevant. It's something to be investigated. There are issues related with the isotropy of turbulence. There are issues related to the isotropy of the particle distribution function, which is also another system, because for the estimate of polarized fraction are typically done by assuming the particles are isotropic in pitch angle. They might not be isotropic in pitch angle, especially if they come from process like driven reconnection, for example. It's not at all obvious that they have isotropized well in the time scale that you observe. These are all things that typically hangs under the carpet of the overall discussion, because you are opening a vast parameter space and sampling it becomes tedious. Let's say, for people like me, for students probably not, but once you're on a certain age, you get bored of trying all this, turning all the wheels of your hidden parameters.
Any other comments? If not, let's sign. Now I'm going to have lunch at the left, and there are a few places left in the table if you want. Thank you very much. Very.